Match-3 games involve swapping colored pieces on a grid to match 3 or more pieces of the same color. You've probably seen lots of Match-3 games on mobile app stores. In this course, I'll be teaching you how to create your own Match-3 game. We'll start with the game board. We'll create a basic game piece, spawn them on a grid, and animate them as they fill up the board. You'll learn how to detect valid matches and clear pieces, or even implement some special game pieces that can clear entire rows or columns, or clear all pieces of a certain color. Finally, we'll turn this into a game by implementing level logic. I'll walk you through implementing 3 unique level types. We'll also implement a user interface for the game, as well as a level select screen where players can choose a level and view their high scores. We've had a lot of ground to cover, so if you're ready, let's get started. This course expects you to be very comfortable in Unity and C# and have a strong understanding of object-oriented design and the Unity API. We'll be using pre-made assets so we can dive deep into the code and logic needed to make a Match-3 game. While we will be touching on some other Unity systems, like animation and UI, the main focus of this course will be on the logic behind the game. I'll be doing my best to explain everything as I go along, but if at any time you feel stuck or would like more information, you can check out my course, Scripting Unity in C#, which goes into more specific detail on how to program in Unity. If you want to brush up on your C# or have questions about C# syntax, watching C# Essential Training is a good option. This course also heavily employs object-oriented design, so if you're having trouble understanding how the system is designed, try watching Foundations of Programming, Object-Oriented Design. Finally, if you'd like to learn more about working with 2D games in Unity, check out Unity 5 2D Essential Training. This course has exercise files containing Unity projects, assets, and code samples. The Unity project folder can be opened in Unity, or you can double-click on one of the scenes in the Scenes folder to open the project. Occasionally, I'll be copy and pasting some code I've already written, and you can find that in the code snippets file. Our game will take place on a grid that holds all the game pieces. When you clear pieces from the grid, new ones will fill in from the top. I've opened up the main scene in the exercise files, and I just have a camera, a sprite with a background texture, and a grid object with a grid script. The project also has some other assets we'll need, like textures and a generic piece prefab that we'll build on later. If you open up the good script, you can see that it doesn't have much in it right now, but we're going to add to it to create a grid to hold and display all of our game pieces. We'll start by adding some parameters that we can adjust in the inspector. Right now, I'm adding 2 integers, which are going to be the X and Y dimensions of our grid. This will let us control the size of our grid. If you save the file and go back to the editor, look in the inspector, you can see that we can set these values here. So go ahead and enter 9 for both, which will give us a 9 by 9 grid. Going back to the grid script, the grid needs to know what type of pieces we can have in it. I'm going to add an enum for the piece type. Right now we just have one piece type, which is the normal type. I'm also adding count, which is just so we know how many different piece types there are. We want to associate each piece type with a prefab. We can do this by using a dictionary, which associates a key, which will be our piece type, with a value, which will be a game object. At the top, add using systems.collections.generic, so we have access to the dictionary class. We'll then define a private dictionary, which has keys of piece type and values of type game object. The reason I made this private is because dictionaries can't be displayed in the inspector. We'll need to create a struct with our key and value and have an array of those instead. I'm creating a struct called piece prefab that has a piece type and the game object. I'm also going to add the system.serializable flag so that our custom struct will show up in the inspector. Now that I defined our struct, we can have an array of them that we can edit in the inspector. Go ahead and save and go back to the editor. Expand the piece prefabs array and set the size to 1. Here we can assign a prefab for the normal type of game piece. Go to the prefabs folder and drag in the normal piece prefab object. to the prefab variable in the inspector. This now associates this prefab with the normal game piece type. Now, like I said before, we want to use a dictionary, but dictionaries can't be displayed in the inspector. What we'll have to do is copy their values from our piece prefab array, which we set in the inspector, into our private dictionary object. First, I'll instantiate our dictionary as a new dictionary with types piece type and game object. And then I'll loop through all of the prefabs in our piece prefabs array. Since the dictionary should only contain one value for each key, we first check if the dictionary already contains a key. Remember that our key is our piece type, and our value is our game object. If it doesn't already contain the key, then we add a new key value pair to our dictionary. Now, we want to display a background behind each of our pieces to make them easier to see. So we'll expose another game object in the inspector that we can assign. Go back to the editor, then in the inspector, drag the piece BG prefab to the background prefab variable. Now that we have a reference to the background prefab, we can instantiate it for each cell of the grid. We first loop through all the rows from 0 to the X dimension, and then we loop through all the columns from 0 to the Y dimension. Then for each cell of the grid, we instantiate our background prefab. We pass in the reference to our background prefab, and the position where we want the prefab to be instantiated. In this case, we want the position to be the X and Y values from our loop. And finally, we pass in the rotation. Quaternion.identity just means that it's not rotated at all. And finally, we'll make this new background a child of our grid object. If you go in the editor and hit play, you can see that we have a background tile for each cell of the grid. Next, we'll look at how to place a game piece on top of each of these background cells. Now that we have our background tiles, let's add some game pieces. Go ahead and open up the grid script. We need an array to hold all of our pieces. Since the grid has 2 dimensions, we'll create a 2D array of game objects. You can create a 2D array by using the comma notation. In Start, we'll instantiate all of our game pieces in the grid, just like we did with the background pieces. First, I'll instantiate my game object array. Tab dimensions the same as my grid. The reason we're storing an array of the game pieces when we didn't store an array of the background pieces is because we'll later want to manipulate the game pieces. The background pieces, once we've created them, can just stay where they are. Again, I'm going to loop through all of the rows in our grid, and then I'm going to loop through all the columns. I'm then going to instantiate a new game object and assign it to our pieces array. I get a reference to the prefab for the normal piece type by using our dictionary. And I'll instantiate the game object at the X and Y coordinates of the grid. I'm then going to change the name of the game object just so it's easier to tell which piece is which. And finally, I'm going to make the piece a child of the grid. Go ahead and hit Start, and we can see that a piece is created on top of each background. However, they're off-center. We'll need to offset the position of the pieces to center the grid. To do that, we're going to create a function called getWorldPosition that will convert a grid coordinate to a world position. What I'm doing here is getting the X position of the grid, which is the center of the grid, and subtracting half of the width to get the left edge of the grid, and then adding our X coordinate. Since our world units are the same spacing as our grid units, this will give us the world position for our game piece. I do the same thing for the Y coordinate, except I invert the pluses and minuses so that our grid starts at the top. Now we'll just update our calls to instantiate for the game pieces and the background pieces to use our new getWorldPosition function. Now if you hit play, the game pieces are nicely centered on the screen. If I move a grid object around, all the pieces move with it. Now we've got our grid set up, let's add some more functionality to our game piece. Next, we'll create our normal game piece. This piece can come in 6 different colors, and when 3 or more of the same color are in a row, they'll disappear. We'll worry about matching and clearing pieces later. For now, we'll define only the most basic functions of the game piece. In the Scripts folder, right-click, and from the menu, select Create, through SharpScript and name it Game Piece. Click on the Prefabs folder and select the normal piece prefab. Go back to the Scripts folder and drag the Game Piece component over to the inspector to add it to our prefab. Now go ahead and open the Game Piece script. To start with, we know that each game piece will have an X and Y coordinate on the grid, so we'll add those first. I created two private ints, X and Y, and then public properties for them. Notice that we only provide a getter for their position. This is because not all pieces will be able to move, so not all pieces should allow their position to be changed. In just a moment, we'll create a movable piece. We also know that each piece will have a type. Right now, we only have the normal piece type, but later we'll have other types. Like I did with the position, I created a private type variable and then a public property to access that variable. I didn't add a setter because we don't want other classes changing our piece type. The game piece should also have a reference to our grid class, in case it needs information about the grid or about other pieces on the board. Like I did before, I created a private variable and a public accessor. I called it gridref because grid with a capital G was already taken by our class. Finally, we'll create an initialization function called init. We'll call this function after we instantiate the game piece's game object so that we can initialize some of these variables. Pinit function takes in the X and Y positions, the grid, and the piece type, which are all the parameters we defined earlier. I use an underscore just to differentiate between the parameters passed into the function and the parameters for our piece. Since we're inside the game piece class, we can set these parameters directly, since we don't have a setter. Open up the grid class, and let's modify how we create the pieces to use this new game piece class. Instead of storing the game object for each piece, we'll store the game piece component. All I'm doing now is switching our array from game objects to game pieces. I'll store the game object in a temporary variable called newPiece. Since we're not storing the game object in the pieces array anymore, I'll replace all the references to it with newPiece. And now we store the game piece component of the newPiece game object in our pieces array. And finally, we call the init function that we just wrote. I'm passing in the X and Y coordinate, this, which is a reference to this grid class, then the piece type, which will just be normal for now. It accidentally auto-completed these brackets, so I'm just going to erase those. If you hit play, you can see that not much has changed, but on the back end, we're now using a custom game piece class instead of storing the game object. Next, we're going to make our pieces move. Now that we've got our basic game piece script, let's add some more features to it. We'll stop at making our pieces movable. In the scripts folder, right-click and create a new C# script and call it movable piece. This movable piece script is a component that will allow us to add mobility to any type of piece. Click on the prefabs folder and select the normal piece prefab. Go back to the scripts folder and drag the movable piece component onto the prefab. Open the movable piece script. The movable piece component needs to know about the game piece that it's attached to, so we'll add a reference to the game piece script. In awake, we'll get the reference to the game piece. I'm using awake to make sure that we get this reference as soon as possible, so that we don't have any no reference exceptions. Then we just need to add a move function, which moves the piece. For now, we'll just instantly move the piece to its new position. Later, when we get to filling the board, we'll animate the pieces. To move the piece, we need to update the X and Y coordinates in the grid, as well as the position of the game object in world space. Updating the coordinates on the grid is easy, though the X and Y properties from the game piece script. The grid has a getWorldPosition function that we wrote earlier, and we can use that to get the position for the game object. We're setting the position locally because the piece is a child of the grid. Since we originally wrote getWorldPosition just for the grid class, it's private. If we want to access it in this movable piece script, we have to make it public. Looking at this, you might notice an issue. Remember that we didn't define a setter for the game piece's position. So we'll need to go back and add that. But we only want to set the X and Y if the piece is movable. If it's not movable, other classes should not be able to update the position. We can check if a piece is movable by seeing if it has the movable piece component. First, we'll get a reference to the movable piece script. Here I've just created a private variable, movable component, and a public property, capital movable component. Then in awake, we'll get the reference to the movable component if the game object has one. If the game object doesn't have a movable piece script on it, this will just return null. So to check if a piece is movable, we just need to see if the movable component variable is null or not. We'll create a function isMovable to do that. If the movable component is not null, meaning it exists, this will return true, meaning a piece is movable. Otherwise, it will return false. Now back to the setter for our position. We only want to set the value if the piece is movable, so we'll use our isMovable function to check that. And we'll do the same thing for the Y property. I'm just going to copy and paste. And I just update the variable X to Y. To check if this all works, let's go back to the grid class and change all the pieces to start as 0, 0. To do that, we just replace getWellPosition with vector3.0. Go back to the editor and hit play. You can see that all the pieces are stacked on top of each other in the center. Now let's use our move function to move the piece to the correct spot. We first check if the piece is movable, and if it is, we use the movable component to move it. Hit play, and you can see that all the pieces are now in the correct place, so our movement code is working. While our game board might not look much different, this movement code will be the basis for our animation once we start filling the board. Next, we'll add support for different colored game pieces, and this is where things get really flashy. Click on the scripts folder, right-click, and create a new C# script called Color Piece. Click on the prefabs folder and click on our normal piece prefab. Go back to the scripts folder and add the color piece script to our prefab. This is going to work just like our movable piece component, except it will set the color of the piece instead of moving it. Open up the color piece script. The first thing we need to know is all the different possible colors. I'm going to use an enum for that. Here I've added all the different possible colors, plus any, because later we'll have pieces that can match with any color. Next, we need an array where we can assign a sprite for each color. I'm creating a struct called colorSprite to hold our color type and our sprite. And I'm going to have the system.serializable flag so that our custom struct can be displayed in the inspector. Finally, I'll add a public array of colorSprite objects so that we can assign them in the inspector. Save and go back to the editor. Click on the normal piece prefab. In the inspector, expand the colorSprites array and set the size to 6. In the textures sprites folder, you'll see sprites for each different color. Go ahead and assign the sprite for each color in the inspector. Yellow sprite for the yellow color, purple sprite for the purple color, etc. Since our normal piece has to be one of these 6 colors, we won't worry about the any color type for now. Go back to the color piece script. Just like we did with the piece type prefabs in the grid, we'll convert this array to a dictionary for faster lookup. At the top of the file, add using system.collections.generic to give us access to the dictionary class. I'll then define a private dictionary with types color type and sprite. In awake, I'll loop through our colorSprites array and add the keys and values to our dictionary. First, I'll instantiate our colorSprite dictionary as a new dictionary with types color type and sprite. I loop through all the structs in our colorSprites array. I check if the dictionary already contains the current key, since dictionaries should only have one value for each key. If it doesn't contain it, I'll go ahead and add the key value pair. Now we have a dictionary mapping colors to sprites. The last 2 properties we need are a property for the color of the piece and a reference to the sprite. Knowing the color of the piece will allow us to easily compare to other pieces for a color match, and having a reference to the sprite will allow us to change it. Here I've created a public property for a color variable with a getter and a setter. The setter calls a function setColor, which we'll define in a minute. I'm also going to add a variable to store the sprite renderer. I'll get a reference to the sprite renderer in awake. I use transform.find to find the child game object amped piece. If we drag our normal piece prefab into the scene, you can see that the sprite renderer is on this game object called piece. Go ahead and delete that. So once we've found the piece game object, we can get the sprite renderer component. Finally, we just had to fill out the setColor function. We set our color property to the new color, and then check if our color sprite dictionary contains a key for the new color. If it does, we assign the sprite of the sprite renderer to the value stored in the dictionary for that color. This will change the sprite of our game piece depending on what color it is. We now just have to tell our grid to create different color pieces. We'll add one more property to color piece to get the number of possible colors. This just returns the length of our color sprites array that we set in the inspector. Open up the game piece script and add a reference to our color component, just like we did with the movable piece component. I'm going to copy and paste and replace all the references to movable piece and movable component with color piece and color component. In awake, we'll get a reference to the color piece component, just like we did with the movable piece component. And finally, so we can check if a piece is colored or not, we're going to add a function that returns a Boolean similar to what we did with isMovable. We'll call it isColored. This will return true if the color component is not equal to null, meaning that it exists. The last step is to open up the grid piece, and after we initialize the piece, set the color of it. We check if the piece is colored, and if it is, we set the color of it to a new random color. Remember that a color type is an enum, meaning it can be converted to and from an integer. So, we just need to get a random integer in the range from 0 to the maximal number of colors. Save everything, go back to the editor, and hit play. Now we have a board full of colorful fish. The next step will be filling the board and animating our pieces as they move.
One of the key things our grid needs to be able to do is refill itself when pieces are cleared. The first step to achieving that is creating an empty piece type so we can add empty spaces in our grid. Drag the normal piece prefab into the scene from the prefabs folder. Our empty piece type will be a stripped down version of this. With the prefab selected, go to the Game Object menu and click Break Prefab Instance. This way, we won't modify our normal piece prefab. Go ahead and rename the game object to Empty Piece Prefab. Remove the movable piece and color piece components in the inspector. Inside the prefab, delete the piece object so we're left with just the root game object. Drag this to the prefab folder to create a new prefab, and then delete the object from the scene. Open up the grid script. We're going to add a new piece type called empty to our piece type enum. Save that and go back to the scene. Click on the grid object. In the piece prefabs array, change the size to 2. Element 0 is going to be our empty piece type. Drag the empty piece prefab from the prefabs folder into the inspector. Element 2 will be our normal piece type. Do the same for the normal piece prefab. We'll have our board start empty and then fill up with pieces at the start of the game. To make our lives easier, let's create a function to spawn a new piece. Go back to the grid class. Create a new function called spawnNewPiece that returns a game piece. This function will take the x and y coordinates of the piece in the grid, as well as the piece type. First, we'll instantiate a new game object. We get the prefab from the prefab dictionary based on the piece type, and we get the position using getWorldPosition. And we make the new piece a child of the grid. Finally, we store the game piece component in our pieces array. We then initialize the piece. Finally, we return the new piece. In the grid start function, we'll change it so that instead of creating normal pieces, we're creating empty ones. We'll use our new spawn new piece function for that. We can replace all this code with a call to spawn new piece, and the piece type will be empty. Hit play, and you can see that the cells are all empty now. Next, we'll write a function to fill in the empty pieces. Now that our board is completely empty, we need to fill it in. Open up the grid script. I'm going to create two function stubs, one called fill and one called fill step. Fill step will only move each piece one space, while fill will call fill step until the board is filled. Fill step will return a boolean. It will be true if any pieces were moved, and false if not. That way, fill knows when the board is filled. I'm going to copy the code for fill step from the code snippets, and then we'll go over it. Fill step starts with a boolean called moved piece, which is false. If we encounter a piece that we need to move, we'll set it to true. We end by returning moved piece. First, we loop through all the columns in reverse order, meaning from bottom to top, since our top is 0. We start a y index at the y dimension -2. Now the reason we do this is because our array is 0 indexed, so there isn't an element at y dim. It's actually from 0 to y dim -1. The reason it's y dim -2 is because we don't care about the bottom row, where we're looking for pieces we can move down, and the bottom row can't be moved down, so we can just ignore it. Then we loop through all the rows. The way these nested loops are set up means that we'll be going through each element in each row, and then on to the next row, going from bottom to top, ignoring the bottom row. We get the game piece at the current position and check if it's movable. If it's not movable, it means we can't move it down to fill the empty space, so we can just ignore it. We get the piece below the current piece, which is at x, y plus 1, remember 0's at the top, and we check if it's empty. If it is empty, then we'll move a current piece down into the space below it. We do that by calling the move function in the piece's movable component, and then setting the piece at x, y plus 1 to the current piece. Remember, that's at xy. We then spawn a new piece at xy that's empty. Remember, since we moved the current piece down, the space where it was will now be empty. Basically, we're swapping a movable piece with an empty piece below it. And since we moved a piece, we set moved piece to true. The top row is a special case, since empty spaces there will be filled by creating new pieces. After checking all the rows, which we just did, we'll recheck the top row to see if it has any empty spaces. Again, I'm going to copy some code from the code snippets and paste it below those for loops. We loop through all the cells in the row. Now, this is where I can get a bit tricky. Remember that what we did before was find a piece, check if the piece under it was empty, and then move the piece down. Well, right now, there aren't any pieces above the first row. So what we do is basically create a piece in this non-existent -1 row and then move it down into the first row. So our piece below will be at the x coordinate and then in the 0th row, which is the top row. We see if it's empty, and if it is, we create a new piece. Now the reason I'm not using spawn piece here is because we're doing this weird negative row thing. So what I do is I instantiate the piece at the x coordinate in the -1 row. I assign this new piece to the x coordinate in the 0th row of our pieces array, since obviously our array can't have a -1 index, and since the new piece will be moving into the 0th row anyway. When I initialize the piece, I pass a -1 for the y coordinate so that we can move the piece from -1 to 0 and it'll animate nicely later. Finally, I move the piece to its new coordinate, which is x in 0, the first row, and set the color to a random color. Now we just have to call fill step until the board is filled. This while loop will call fill step, and if it's true, it will just keep calling fill step until it returns false, meaning we didn't move any pieces. With that done, we now just have to call fill in the grid start function. Go to the editor and hit play. You can see that the board is now filled. However, it would be nice if this didn't happen instantaneously. We want the pieces to look like they're falling down and filling the board, and we'll get to that in the next video. Now we're going to animate our pieces so it looks like they're actually falling down from the top of the board instead of just appearing instantly. To do this, we'll need to change our fill function to be a coroutine. A coroutine is a function that can execute across multiple frames versus a regular function which has to execute in one frame. Open up the grid script. We first change the return type of our fill function to be IEnumerator, which means it's a coroutine. We also need to change how we call fill, since coroutines must be started with start coroutine. Next, we're going to add a new parameter called fill time, which is the time between calls to fill step. A lower fill time means the board will fill faster, while a higher fill time means it fills slower. Now we just wait that many seconds in between calls to fill step. That way, our fill will happen gradually over time. We can do that using yield return new wait for seconds. Hit save and go to the editor. Click on the grid object in the scene and set fill time to something small, say 0.1, and go ahead and hit play. You can see as each row of the board is filled, but this still looks a little choppy. Each piece needs to animate as it moves from space to space. To do that, we'll change a move in the movable piece script to also be a coroutine. To start, we're going to create a new variable to store a reference to our move coroutine. First, we'll add a function to store our move coroutine. This way, we can stop the coroutine if we get another move command before we finished animating. The move function now just becomes a wrapper that starts and stops the coroutine. If our stored coroutine is not null, go ahead and stop it using stop coroutine. Then we get a reference to a new coroutine. I'm using a function called move coroutine, which I'll define in a minute. The last thing we need is how long the animation should take. Add a new parameter to the move function, which is a float telling us how many seconds the animation should play for. We'll also pass the parameter to our move coroutine that we're going to write in a bit. Head back to the grid script and update all the calls to move to pass in a time. In this case, we're going to use our fill time so that the time it takes the board to refill is the same amount of time it takes a piece to move from one space to the next. Now we'll write the move coroutine. Again, this will return an IEnumerator, and the signature is the same as our move function. The move coroutine is going to interpolate between the starting and ending positions for the piece, moving it a tiny bit each frame. Our starting position is simply our transform's current position, and we can get the ending position using the grid's getWorldPosition function with new x and new y. Next, we're going to interpolate between start pause and end pause. Interpolation is getting a value in between two other values based on a parameter which we'll call t. For example, if t is 0, then the interpolation would return the starting position. If t is 1, it would return the end position. And if t was 1/2, it would return something in between start pause and end pause. We're going to loop over values of t from 0 to however long our animation should take, incrementing t by time-delta time each frame. Time-delta time is the amount of time the last frame took. The reason we're looping t from 0 to time instead of from 0 to 1 is because this way our animation will take exactly time seconds to execute. We then set the position of the piece to our current interpolation. We divide t by time to get a value between 0 and 1. And yield return 0 just waits for one frame. At the end of the loop, we'll set the position of the piece to our ending position, just in case our loop didn't get all the way to end pause. That takes care of our animation, so now we just need to set our x and y parameters to new x and new y. Go ahead and hit play, and you can see that all the pieces nicely animate in. However, if you look at the object hierarchy, you might notice a problem. There are tons of empty pieces even though the board is filled. This is because we're not cleaning up the empty pieces before moving the new piece into it. This is why it's so important to clean up objects when you're done with them. Luckily, this is easy to do in Unity using the destroy function. In the grid class, we'll simply destroy the empty piece below before moving a new piece into it. Remember that we're storing the game piece component of each piece, so to destroy the whole object, we need to call destroy on the piece's game object. Now when we look in the hierarchy, All the empty pieces are gone once the board is filled. Now that our grid is done, we can have some more fun with our Dane pieces. Next, we're going to be creating an obstacle game piece.
We're not going to create a special type of piece that doesn't move. This piece is an obstacle that our normal pieces will have to fill around. First, we need to create a new prefab, just like we did for the empty piece. Drag the normal piece prefab into the scene from the prefabs folder. Select Game Object, Break Prefab Instance, and rename it to Bubble Piece Prefab. Remove the movable and color components in the inspector. Open the prefab, click on the piece game object, and replace the sprite with Bubble01. Drag the Bubble Piece Prefab object into the prefabs folder to create a prefab out of it, and then delete it from the scene. Open the grid script and add the new bubble piece type to our enum. Save that and go back to the editor and click on the grid object. Change the size of the piece prefabs array to 3. Set the type of the last element to bubble and drag the bubble piece prefab from the prefabs folder into the prefab variable. To test out our bubble piece, we'll create one in the center of the grid in the grid start function. First, we'll destroy the empty piece at the center of the grid, and then spawn a new bubble piece there. Go back to the editor and hit play. You can see that the pieces get stopped by the obstacle. Right now, no pieces can go below the bubble, but in the next video, we'll see how to fill the space below the obstacle. In addition to moving straight down to fill a space, pieces can also move diagonally. This lets pieces fill in under obstacles. We're going to update the fill step function to also move pieces diagonally. In the grid script, we're going to add a new private boolean called inverse. If pieces can fill diagonally, it means there may be more than one piece that could potentially fill an empty space. Since we don't always want the diagonal piece to come from the same direction, we'll swap the direction we're traversing the grid in every step and keep track of which way we're going using inverse. Now we just swap inverse after every call to fill step. Next, we'll update our loop in fill step so that we can change our direction of traversal depending on the value of inverse. I'm changing x to loop x. We'll use this value to calculate the actual x coordinate of our piece. If we're not inverted, x is simply equal to loop x. If we are inverted, then x is equal to the x dimensions minus 1 minus loop x. Essentially, when we're not inverted, we're traversing from 0 to the x dimension. When we are inverted, we're traversing from the x dimension down to 0. Here's our code for moving straight down into an empty space. If we can move straight down, we're not going to bother checking if we can move diagonally. So our code for moving diagonally is going to go in an else statement. Get the code for moving straight down fails. I'm going to copy the code for moving diagonally from the code snippets file, and then we'll go over it. What we're doing here is looping through our two diagonals, down left and down right. If the value of diag is 0, this means it's the piece directly below us, which we already checked for up here, so we don't have to worry about it. Diag x is the x coordinate of our diagonal piece. Depending on the value of diag, this will be either to the left or the right of our current piece. For example, when diag is -1, this piece will be to our left, and when it's 1, it will be to our right. If we're inverted, then it will be the opposite. We check if the x coordinate of the diagonal is within the bounds of our board, and if it is, we get a reference to the diagonal piece, which is our y plus 1, the row below us. Now, we obviously can't move into a piece if it's not empty, so we check to make sure that the diagonal piece is empty. Next, we need to look at the pieces above the diagonal piece. The reason for this is, if there's another piece above the empty diagonal space, it can just move straight down to fill the space. We don't want to move diagonally unless there's no pieces above the empty space that can fill it. We loop through all the pieces above the diagonal space. If we count our movable piece, we break out of the loop, since this piece can simply fall down and fill the space. If we count our piece that's not movable and that's not empty, for example an obstacle, it means that this empty space is blocked and won't be able to be filled from above. If the piece can't be filled from above, then we'll fill it diagonally, and the code for this is the same as the code that we used to fill from the top down. Now when we run the game, the pieces fill in below the bubble. Try adding some more bubbles to see how the pieces fill in below them. I have code to create some bubbles in the code snippets. You can use this or just put them wherever you like. I'm placing this in start where we initially created the single bubble. And I'm just creating lots of bubbles in the 4th row as well as one in the top row. And as you can see, the pieces fill around all the bubbles. There are a few empty spaces that can't be filled even with diagonal filling. These will remain empty until we get to clearing the bubbles, which will be in a later video. Now that our grid is all set up, we're ready to start matching and clearing pieces.
Now that we can fill our board with pieces, we need to be able to match and clear them. A player clears a piece by swapping it with an adjacent piece to match 3 or more pieces of the same color. They swap a piece by clicking and dragging from one piece to another. To detect mouse clicks, we need to add a collider to our game piece. Drive the normal piece prefab into the scene. From the Component menu, select Physics 2D, Box Collider. This box collider will allow us to detect mouse clicks on the piece. The collider is represented by this green box. Since our sprites are anchored to the top left corner, we'll need to offset it. Setting the X offset to 0.5 in the inspector and the Y offset to -0.5 aligns the collider with our sprite. In the inspector, hit Apply to apply this to all of our prefabs. And then go ahead and delete the object from the scene. Open the GamePuse script, and we're going to add some functions to detect mouse clicks. These functions are onMouseDown, onMouseEnter, and onMouseUp. We'll just stub them out for now. As the name suggests, onMouseDown is called when the mouse is pressed inside an element. onMouseUp is called when the mouse is released. And onMouseEnter is called when the mouse enters an element. Open the grid script. The first thing we need to swap 2 pieces is to know if they're adjacent. Create a new function called isAdjacent, which takes 2 game pieces and returns a boolean. 2 pieces are adjacent if their row is the same and they're in adjacent columns, or if their column is the same and they're in adjacent rows. This returns true if piece 1 and piece 2 have the same x coordinate and their y coordinates are within one space of each other. Next, we'll do the same thing, but if the y coordinates are equal and the x coordinates are within one space of each other. We also need a function to swap the 2 pieces if they're adjacent. Create a new function called swapPieces that takes 2 game piece objects. We'll only swap the pieces if they're both movable. If they are, then we assign them to each other's positions in our pieces array. We then move the pieces from one space in the grid to the other. We'll store the x and y coordinates of piece 1 in these temporary variables so that they don't get overridden when we move the piece. We move piece 1 to piece 2's position and piece 2 to piece 1's position that we stored earlier. And that's it for the swapPieces function. Now we just need to trigger it when the mouse is pressed. We need to know what piece we've clicked on and what piece we let go of the mouse on. Create 2 new private variables to store these pieces. One is the piece that we've pressed down on, while the other is the last piece that our mouse enters the bounding box of. Now we'll assign these variables when someone clicks on the mouse or moves the mouse over a piece. Create 2 public functions, one for when we press on a piece and one for when we enter a piece. These will pass in the game piece that was clicked on or the mouse was hovered over. Later, we'll have our game piece call these functions. In press piece, we set our pressed piece variable, and in enter piece, we set the entered piece variable. So we know the piece that the player pressed on, and we know the piece that they're hovering over. All that's left is to do the swap when they release the mouse. Add one more function for when they release the mouse. Here's where our isAdjacent function gets put to use. We check if the pressed piece and the piece that we were hovering over are adjacent to one another. And if they are, we swap them. Now we just need to trigger these functions from our mouse events in GamePiece. This is a reference to this GamePiece component, which is the game piece that we clicked on or hovered over. Go to the editor and try swapping some pieces around. As you can see, you can swap any two adjacent pieces. Next, we'll make it so that you can only swap pieces if they create a match. Right now, the player can switch any two game pieces. We want to make it so that the player can only move the piece if it creates a match. A match means 3 or more pieces in a row of the same color. This can mean 3, 4, or 5 pieces in a straight line, or it could be 2 intersecting rows of 3 pieces, creating an L or T shape. Or add a function to the grid class to determine if a match can be made with a given piece. For starters, we'll just worry about matching pieces in a straight line. In the next video, we'll handle matching pieces in an L shape. Open the grid class and create a function called getMatch, which takes a game piece and the new position the piece is moving to. This function will return a list of game pieces that are part of the match. If no match is found, it will return null. First, we need to check if the piece is colored, since only colored pieces can be matched. We then create some variables to store adjacent pieces of the same color, so we can check if we have enough pieces to form our match. We'll also store the piece's color, so we can reference it later. We have a list of adjacent pieces in both the vertical and horizontal directions, and a list of pieces that ended up being part of the match. What we're going to do is traverse through the adjacent pieces, first horizontally, meaning left and right, and then vertically, meaning up and down. Each adjacent piece we find that is the same color will get added to the array of potential pieces, either horizontal pieces or vertical pieces, depending on which way we're going. We'll stop when we run into a piece that is a different color. At the end, if we have enough pieces to form a match, they'll get added to the matching pieces list. First, we'll add this piece to our list of potential pieces, since we know that this piece will be in any potential match that we find. Next, we have a loop that simply changes which direction we're going. When dir is 0, we'll go one way, and when dir is 1, we'll go the other way. Next, we need to loop through all of the adjacent pieces. X offset is how far away the adjacent piece is from our central piece. We'll now calculate the actual x coordinate of the piece. If dir is 0, which means we're going left, the x coordinate is new x minus our offset. Otherwise, if we're going right, the x coordinate is new x plus our offset. If the x coordinate goes outside the bounds of our grid, we break out of the loop. Finally, we check if the adjacent piece is a match. Remember, we're traversing horizontally right now, so the x coordinate of the adjacent piece is the same as our central piece, new y. We check if the piece is colored, and if the color is the same as our current piece. If the piece is a match, we add it to the horizontal pieces list. Otherwise, we've run into a piece that isn't a match, which means we stop traversing in this direction. Once we're done, we check the horizontal pieces has enough pieces in it to form a match. Remember, the minimum number of pieces needed is 3. If we have enough pieces for a match, we go ahead and copy them into the matching pieces list. Finally, if we have enough matching pieces in the matching pieces list, we can return it. If we don't have enough pieces to form the match, we'll traverse again, but this time vertically. I'm going to copy the code for horizontal traversal, and then we'll update it for vertical traversal. We change horizontal pieces to vertical pieces, and all the places where it says X we change to Y. When dir is 0, we'll be traversing up, and when dir is 1, we'll be traversing down. Next, we just update the coordinates of our adjacent piece. Since we're traversing vertically, the X coordinate is the same, and the Y coordinate is the one that we just calculated. If we find a matching piece, we add it to the vertical pieces list. And again, if we have enough pieces to form a match, we'll add it to the matching pieces list. If matching pieces has enough pieces to form a match, we return it. If not, it means that no match was found with this piece, and so we return null. Now all that's left is to update the swap piece function to only allow swaps if the move creates a match. We check if either of the swapped pieces creates a match. If either of these return non-null values, it means we have a match. We'll put the rest of the swap pieces code inside that if statement. If we end up not having a match, we go ahead and swap the pieces back to their original positions in the array. I'm parentheses in the wrong place. All right, head to the editor, hit play, and try swapping some pieces around. You see that you can no longer swap pieces if they don't make a match. That did make a match, so we could swap it. Next, we'll add support for matching pieces in an L or T shape. Our getMatch function currently always supports matches in straight lines. If we tried to clear pieces in an L shape, it would only clear the pieces in one direction. We can improve on this function to make it so that we can also match pieces in L or T shapes. L or T-shaped matches occur when we have two straight lines of 3 pieces that share one piece. We're already determining if we have 3 in a row in one direction. Now when we find 3 in a row, we just need to check for a row of 3 in the perpendicular direction. Open up the grid class and look at getMatch. We start off by checking for matches in the horizontal direction. If we find a horizontal match of 3, we now need to look for a vertical match of 3 containing one of those same pieces. This code will be very similar to the code for horizontal traversal, except for one main difference. Since we don't know which piece is the one shared between the two directions, we need to loop through the 3 pieces in our horizontal match and check each one. For each piece in the horizontal match, we traverse vertically up and down to see if we have enough pieces for a vertical match. First, we check if we found a horizontal match. If we did, then we iterate through all the pieces in the horizontal match. We then do the same thing we did when we were traversing horizontally. We have a loop to change the direction. And we then iterate through all the adjacent pieces in that direction. If dir is 0, we check up, and if dir is 1, we check down. If the coordinate of the adjacent piece is outside of our grid's dimensions, we break out of the loop. We check if this adjacent piece is colored and if the color matches. Since we're traversing upward from one of the horizontal pieces, the x-coordinate of the adjacent piece is the x-coordinate of the horizontal piece we're currently traversing. The y-coordinate is the y that we calculated above. If the piece matches, we add it to the vertical pieces list. If the piece doesn't match, we break out of the loop. After traversing vertically up from one of the matching pieces, we check if we have enough vertical pieces to form a match. We only need 2 vertical pieces to form a match, since we know that this horizontal piece will also be included in the match. If we don't have enough vertical pieces for a match, we'd clear the vertical pieces list so that we can get ready to iterate along the next horizontal matching piece. If we have enough pieces for a match, we'll add them to the matching pieces list. Since we found a match, we can stop searching and break out of the loop. If at this point matching pieces contains enough pieces to form a match, we can return. If not, we repeat the same process again, searching vertically first, and then horizontally if we found a vertical match. We clear the horizontal and vertical arrays to get ready to traverse again. I'm going to copy the code that we just wrote for traversing vertically to look for an L shape, and paste it down here and update it to traverse horizontally. I update all the references to horizontal pieces with vertical pieces, and all the references to Y with X. When direction is 0, we search to the left, and when it's 1, we search to the right. Next, we just update the index of the adjacent piece. The x index is the one we calculated above, and since we're traversing horizontally from one of the vertical matching pieces, the y-coordinate is the y-coordinate of the current vertical piece that we're looking at. Finally, we check if we have enough pieces for a match, and if so, copy the pieces from horizontal pieces to matching pieces. And if matching pieces has at least 3 elements, then we return it. Otherwise, there is no match and we return null. Next, we'll put this code to use to actually clear the match that we found.
Now that we can detect valid matches, we can start clearing the matching pieces. First, we're going to make a quick animation for when a piece is cleared, creating a folder called Animations. Inside that folder, create a new animation by right-clicking and going to Create, animation. Call it normal piece clear. Next, go to the prefabs folder and drag in the normal piece prefab. Go back to the animations folder and drag in the animation we just made over the normal piece prefab in the hierarchy. You can see that this added an animator component to our prefab. This will allow us to play our animation. It also created an animation controller. The animation controller controls which animation is played. Double-click the animation controller to open it. Here you can see that we have one animation called normal piece clear. This is orange, meaning it's the default state. That means that our animation will play automatically when the game is run, which is not what we want. Right-click and create a new empty state. Right-click on this state and select Set as Layer Default State. That way, when the game starts, our prefab will go into this default state, which is not animated. Later, when we want to clear the piece, we'll transition to the normal piece clear state, which will play the clear animation. Go back to the scene and click on the prefab. Open the animation window by going to Window, Animation. You can delete this missing property. Make sure that we're editing the normal piece clear animation. We're going to add a new property, which is the value that we're animating. Expand the piece menu, and then the transform menu, and go ahead and add the properties for the position of the piece's transform and the scale of the piece's transform. We're also going to add the property for the piece's sprite renderer's color. We're going to scale the piece and make it transparent when we clear it. Expand the scale property. Each of these dots on the right represents a key. Click on the key at the end of the animation. You can see right now the scale is 1. Set the X and Y scale to 1.5. You can see it update in the scene. Drag along the timeline to watch the piece animate. You can see it goes from a scale of 1 to a scale of 1.5. Our piece is anchored to the top left corner, so it scales from the top left corner instead of the center. So we also need to adjust the position of the piece so it appears to be scaling from the center. Click on the last keyframe again and expand the position property. Since we're increasing the scale by 0.5, we need to offset the piece by half of that, 0.25, so it looks centered. Set the X position to negative 0.25 and the Y position to 0.25. The piece appears to be scaling from the center. Finally, we want to animate the piece's alpha so that it looks like it disappears. Click on the last key of the animation. Expand the sprite renderer color property and set the alpha to 0. You can see that the piece goes from completely opaque to completely transparent at the end of the animation. Hit the play button to play the animation. You can see that it's a bit slow. Adjust the number of samples until you get a speed you like. Go ahead and close the animation window. Click on the prefab, and in the inspector, click Apply. This will apply our changes to all of our prefabs. Then go ahead and delete the object from the scene. We'll be using this animation when we clear our piece in the next video. Just like how we created the movable piece and color piece scripts, we're now going to make a clearable piece script. Go ahead and make a new script called clearable piece and open it. The first thing we're going to do is add some variables. Add a variable to hold the clear animation we made in the last video. Our animation is of type animation clip, and I'm just going to call it clear animation. We'll need this so we can play the animation later. We also might want to know if the piece is in the process of being cleared, so we're going to add a boolean to keep track of that called isBeingCleared. Finally, we need a reference to the game piece that we're attached to. This way, we can access properties of the piece and have a reference to the grid object. I'm making this variable protected because later on we're going to extend this class, and the derived classes need to have access to this variable. We'll get a reference to the game piece in awake using getComponent. Now we'll add a function called clear, which we'll call when we want to clear a piece. The clear function will call a coroutine that clears the piece and plays our animation. We'll write the coroutine first. Create a function that returns IEnumLayer called clearCoroutine. play the animation, we need to get the animator component. If we have an animator component, we tell it to play our animation. We can get the name of the animation from our clear animation variable. We then wait for as many seconds as the animation takes to play. The length of the animation is clearAnimation.length. Once we finish playing our animation, we'll destroy the piece. Now we'll write the clear function, which other classes will be calling to clear this piece. The clear function just sets the isBeingCleared boolean to true, and then starts the color team. That's it for the clearable script. Our game piece needs to know if it's clearable, so like we did with the other components, we'll add a reference to the clearable piece script to the game piece class. In awake, we'll get a reference to our clearable component. And then finally we'll add a function to check if this piece can be cleared, just like we did with movable and colored. Go back to the editor and select the normal piece prefab. Add the clearable component by clicking on Add Component and typing Clearable Piece. Drag the clear animation we made from the project window into the clear animation variable in the inspector. Now our piece is ready to be cleared, and we just need the grid to call the clear function. With that clearable piece component all set up, we can now call the clear function to clear a matched piece. Open the grid script. The grid will be responsible for clearing pieces and refilling the board. First, we need a function to clear a piece. We'll call this function clearPiece, and it will take the position on the grid to clear. It will return a boolean, which is whether or not we were able to clear the piece. We check if the piece is clearable, and if it hasn't already been marked for clearing. Then we call clear on the piece, and spawn a new empty piece in its place. We return true if we were able to clear the piece. Otherwise, we return false. Next, we'll clear the function that checks the whole board for valid matches and clears them. We need to check the whole board instead of just the pieces we swapped, because clearing pieces might result in other matches in other parts of the board. This function will return a boolean, which is whether the board needs to be refilled or not. When we clear pieces, we need to tell the board to fill in those empty spaces. We loot through all of the pieces on the board. If the piece is clearable, we check if there's a match. Since we're not moving the piece, the new X and new Y values we pass to getMatch are just the current position of the piece. If we found the match, we loot through all of the pieces in the match and clear them. If we were able to clear the piece, it means the board needs to be refilled, so we set needs refill to true. And finally, we return needs refill. After we successfully swap two pieces, we call clear all valid matches to clear the board. Hit play and make a match. The piece is now clear, but the board doesn't refill. We need to refill the board after clearing the pieces. However, as the board fills, more matches could be made. So we need to update our fill routine to check for matches again once it's done filling. Needs refill is whether or not the board needs to be refilled. The board will need to be refilled if clear all valid matches returns true. If any pieces are cleared, the board will refill again, and the process will repeat until no more matches can be made and the board can't be filled anymore. We'll put another yield at the beginning to give some time between clearing the pieces and refilling them. If you try swapping a piece now, the board will refill. If more matches are made while the board is filling, those will also be cleared. Right now, there's no way to clear the bubble pieces. We're going to add a way to clear them by matching a piece adjacent to them. We'll start by creating a clear animation for the bubble piece, like we did for the normal piece. The only difference is that this animation is going to be made up of different sprites. Drag the bubble piece prefab into the hierarchy. In the Animations folder, create a new animation called Bubble Piece Clear. Drag the animation onto the prefab in the hierarchy. This will add the animator component and create a new animation controller. Double-click the animation controller to open it. Since we don't want the clear animation to play automatically, go ahead and create a new empty state and set that as the default state. Go back to the seam, make sure the bubble piece prefab is selected, and open the animation window. Go ahead and delete the missing property. I'm going to drag the tab through the animation window above the scene view, that way the window won't get hidden behind the editor. Add the piece sprite renderer sprite property. The sprite property is the sprite texture that's currently being displayed. In the texture sprites folder, use the shift key to select bubble 01 to bubble 08, and then drag all of these into the animation window. You can see that it creates a key for each of the sprites. Delete the first and last key, and then drag our 8 frames so that they start on frame 0. I'm now going to pop the animation window back out so we can see our animation in action. Go ahead and hit play. The animation is a bit slow, so go ahead and adjust the sample rate until you get a speed you like. Now that we're done creating our animation, we just have to add the clearable piece component to the bubble piece prefab. Drag the clearable piece script from the private window onto the prefab instance in the hierarchy. For the clear animation variable, drag in the bubble piece clear animation we just made. Click apply to apply these settings to the prefab, and then delete the object from the seam. We're now ready to clear our bubble piece when we make a match adjacent to it. To clear a bubble obstacle, one of the pieces adjacent to it needs to be cleared. Open the grid script and clear a new function called clear obstacles, which takes in the X and Y position of a piece that was just cleared. This function will search for obstacles in the adjacent pieces and clear them. So when we clear a piece with the clear piece function, we'll also clear any obstacles around the piece by calling clear obstacles X, Y. Now let's fill out clear obstacles. First we'll look at all the adjacent pieces to the left and right. If the coordinate is the same as the X value we passed in, we ignore it, since we just want to look at the adjacent pieces. We also only want to look at pieces that are within the dimensions of our grid. We check that the adjacent piece is a bubble type piece, and we check if it's clearable. If it is, we call the clear function and spawn a new empty piece to replace the bubble. The reason we're not calling our clear piece function here is because that is only for normal game pieces. If we call this here, then clearing an obstacle would cause other obstacles around it to also be cleared, since clear piece calls clear obstacle. Instead, we'll call the clear function directly and spawn a new empty piece. Now we do the same thing in the Y direction, checking the adjacent pieces above and below this space. If we run the game and match a piece next to a bubble, the bubble will get cleared. Now that we're able to clear both regular pieces and obstacles, we're ready to move on to creating special pieces. While you only need to match 3 in a row to clear pieces, matching 4 or more in a row creates a bonus piece with special properties. These special pieces will clear an entire row or column when matched. We're going to create 2 new prefabs. One will be a piece that can clear rows, and the other a piece that can clear columns. There will also play a special animation to differentiate them from other pieces and let the player know whether they clear a row or column. Other than that, they will be similar to our normal pieces. Drag the normal piece prefab into the seam. Select it and choose Break Prefab Instance from the Game Object menu. Rename the object to Row Clear Piece Prefab. In the inspector, remove the animator component. We'll be adding a new one in just a minute. In the Animations folder, create a new animation called Row Clear Piece Animation. This animation will move the piece from side to side. The animation lets the player know that this piece clears a row. Click on the animation and check the box for loop time in the inspector. This will make the animation loop. Drag the animation onto the Row Clear object in the hierarchy. This adds a new animator component and creates a new animation controller. Double-click on the animation controller. Since we want this animation to play as soon as the piece is created, it needs to be the default state. The state is orange, which means it's already the default state, and will play automatically. We also want our piece to play a clear animation when we clear it. We'll reuse the same clear animation as the normal piece. Drag the normal piece clear animation from the project window into the animation controller. This will allow us to play the animation when a piece is cleared. Go back to the scene, click on the row clear piece object, and open the animation window. Make sure we're editing the row clear piece animation. The animation will have the piece moving to the left, back to the center, to the right, and back to the center, and then looping. Add a property for the piece object's transforms position. Go ahead and delete the key at the end of the animation. Click on frame 1 and expand the piece property. The piece's x-coordinate starts at 0. To move it to the left, we set the x position to be negative. I'm using negative 0.05, so the piece just moves very slightly to the left. Click on frame 2 and set the x position back to 0. This moves the piece back to the center. In frame 3, we want to move the same amount, but to the right, so we use a positive number. And finally, in frame 4, we set the x back to 0 to move back to the center. Hit play. You can see the fish moves back and forth. If you want to adjust the speed of the animation, adjust the sample rate. Now that we have edited the animation, we can make our prefab. Drag the object into the prefab folder to create a prefab out of it. Now we just do the same thing for the column clearing piece. We drag the novel piece prefab into the hierarchy and break the prefab instance. Then we rename it, and we remove the animator component. Create a new animation called column clear piece animation. Make sure that the loop time box is checked, and then drag this onto the column clear object. Double-click on the new animation controller that was just created, and then drag in the normal piece clear animation. Go back to the scene, make sure the column clear piece object is selected, and open the animation window. This animation will be the same as the last one, except it will move up and down instead of left and right. We add a property for the position. In frame 1, we move up in the positive Y direction. In frame 2, we move back to the center. In frame 3, we move down in the negative Y direction. And then in frame 4, we move back to the center. Also remember to go ahead and delete that last frame. Click play to play the animation. You can adjust the speed by changing the sample rate. Once you're done editing the animation, drag the object into the prefabs folder to create a prefab out of it. Now both of our special pieces are ready to be spawned into the game. We want to spawn one of the two prefabs we made in the previous video when the player matches 4 in a row. Open the grid class and add two new piece types, row clear and column clear. Save and go back to the editor. Click on the grid object, and in the inspector, increase the size of the piece prefabs array to 5. Element 3 will be our row clear piece type, and element 4 will be the column clear piece type. Then drag the prefabs for these pieces into the inspector. When we make the match, we check if the match contains 4 pieces, and if it does, we spawn a new special dam piece. The piece type is determined by the direction the player moved the pieces. If they swapped 2 pieces that were in the same row, they'll create a row clearing piece. And if they swap 2 pieces in the same column, they'll create a column clearing piece. The piece will be spawned at the position of the piece the player moved. If 4 in a row occurred just from filling the board and not from the player swapping pieces, then the piece type and position are random. To determine the piece type, we need to know if the player swapped a piece or not. We can do this by checking the stored pressed and entered pieces. This means that once we finish swapping the pieces, we need to set these values back to null. That way, when we're spawning a special piece, we can check that these are null, and if so, it means that the player did not swap pieces. In the swap pieces function, after we swap and clear the pieces, but before we refill the board, we'll set our store pieces to null. Now in clear all valid matches, we'll determine if we should spawn a special piece, and what type of piece it should be. Special piece type is the type of special piece that we should spawn. It starts out as piece type.count, which doesn't correspond to any piece. If we determine that we should spawn a special piece, then we'll set this to the appropriate value. We also get a random piece from the match, and set the X and Y position of the special piece to its position. If we later determine that the special piece was created by swapping pieces, we'll replace these with the position of the swapped piece. If the match contains 4 pieces, it means we should spawn a special row or column clearing piece. If pressed piece or entered piece is no, it means the match was not cleared by swapping pieces. In that case, the direction of the special piece is determined randomly. If the player did swap 2 pieces, then we'll use that to determine the direction of the special piece. If the 2 pieces are in the same row, then the piece will be a row clearing piece. If the 2 pieces are in the same column, it'll be a column clearing piece. Lastly, if the match was created by swapping pieces, we need to set the position of the special piece to the position of the piece that the player moved. If, while searching through the matched pieces, we find one of the swapped pieces, then we'll set the special piece's position to that piece's position. Next, we'll actually be creating the special piece when a match is made. We've determined what type of special piece to spawn and where to spawn it. Now we just need to create the piece and clear all valid matches after clearing the match. In the clear all valid matches function in the grid script, after clearing the match, we'll check if we should spawn the special piece. If the special piece type is still the default value, which is count, it means we shouldn't spawn a special piece. If the piece type is something other than count, we'll destroy the empty piece and then spawn a new special piece. The color of the row and column clearing special piece should match the color of the pieces that were matched. Since we know all the pieces in the match of the same color, we can just check the color of the first piece and set the color of the new special piece to that. If this new piece is a row or column clearing piece, and if the matched piece is colorable, then we set the color of the new special piece to the color of the matched pieces. The row clear and column clear pieces have one other special property. Usually when you swap 2 pieces, only one of them forms a match. The other one stays on the board. In the case of special pieces, they should be cleared whenever they're swapped, even if it's the other piece in the swap that forms the match. In swap pieces, after we clear all valid moves, we check if either of the pieces involved in the swap were row or column clearing pieces. If they are, then we clear the piece. Run the game and try to match 4 pieces in a row. New special pieces will be created. Right now, if you create a match with them, they just act like normal pieces. But next, we'll be giving them the ability to clear entire rows or columns. Let's change what our special pieces do when we clear them. Instead of doing nothing like the normal piece, they'll clear all the pieces at either the same row or same column, depending on what type of special piece it is. Create a new script called clearLinePiece. Go ahead and open that up. This class is going to extend from clearable piece. This will allow us to store a clearLinePiece component as the clearable component on our game piece. It also lets us inherit all the functions from clearable piece. We're just going to slightly modify the clear function to also clear the row or column. First, we need to know if this piece is one that clears a row or a column. Add a public boolean called isRow. If we're a row clearing piece, this will be true, and if we're a column clearing piece, it will be false. In the editor, select the row clear piece prefab. We're going to replace the regular clearable piece component with the new clearLinePiece component. Remove the clearable piece component, and then click on Add Component and add a clearLinePiece. Since this is the row clearing piece prefab, check the box for isRow. We also need to assign the clear animation, which will just be our normal piece clear animation. I'm going to do the same thing for the column clear prefab. Since this is a column clear piece, I leave the is row box unchecked. Hit play, and you can see that the special pieces still act just like normal game pieces. This is because clear line piece is just using the normal clear function for now. We need to override it with a new function. Open the clearable piece script. In order to overwrite the clear function with our new function, we need to add the keyword virtual. This just lets the compiler know that derived classes might override this with their own functionality. Now in clear line piece, we can override clear. We start by calling the clear function on the base class, which is clearable piece, since we still want that functionality. Then, depending on if this is a row or column clearing piece, we clear either the current row or column. Now we just need to implement functions to clear a whole row or column. Go to the grid class and create a function called clearRow, which takes the index of the row to clear. We iterate through the row and call clearPiece on each piece. We'll create another function called clearColumn that does the same thing, except it clears the whole column instead of the whole row. Now in the clear function and clear line piece, we can call these functions to clear a row or column. Hit play and match 4 in a row to create a special piece. Then match one of the special pieces, and you can see that it clears the entire row or column. Next, we're going to be creating another type of special piece, one that clears all pieces on the board of a certain color. We're going to create a new special piece that clears all the pieces on the board of a certain color. First, we'll make the prefab. Drag the normal piece prefab into the hierarchy, and select Break Prefab Instance from the Game Object menu. We name this to Rainbow Piece Prefab. Instead of having 6 possible colors like a normal piece, this piece will only have 1 color. So change the size of the color sprites array to 1. The 1 color will be any, which can be matched with any piece. You can find the texture for the rainbow piece in the exercise files, under Textures, Sprites. Drag the file called Rainbow Fish into the sprite variable in the inspector. We'll also update the sprite on the piece object. Next, we'll create a new script that will clear all the pieces of a certain color. This is similar to what we did with the clear line piece script. Create a new script and call it clear color piece. Click on the rainbow piece object and remove the clearable piece component. Click add component and add the clear color piece component we just created. Open this script. This class is going to extend from the clearable piece class. We're also going to store a variable, which is the color that we should clear. Since we'll need the access variable from other classes, we create a public property. Finally, we'll override the clear function, just like we did in the clear line piece script. We'll call the clear function on the base class, since we still want that functionality, and then we'll clear all the pieces of a certain color. That will be implemented later. Go back to the editor and assign the normal piece clear animation to the clear animation variable in the clear color piece component. Now we're all done, and we can convert this object into a prefab by dragging it into the prefabs folder. Open the grid script. Add a new rainbow piece type. Back in the editor, click on the grid object. Increase the size of the piece prefabs array to 6. The last element will be our rainbow piece prefab. Go ahead and drag the rainbow piece prefab into the inspector. You can then delete the rainbow piece prefab from the scene. Now that we've created our rainbow piece prefab, we need to spawn it when the player matches 5 or more pieces in a row. Now that we've created our rainbow piece prefab, we need to have the grid clear all the pieces of a certain color, and also spawn the rainbow piece when the player matches 5 or more pieces. Open the grid script. Add a new function called clearColor, which takes in the color to be cleared. This function will loop through all the pieces in the grid. We first check if the piece is colored. If it is, we check if the color of the piece matches the color passed into the function. Or we check if the color passed in is any. If we pass in the color any, it can clear any piece. If the piece is a match, we clear it. Open the clear color piece script. We'll finish filling out the clear function. Call the clear color function we just added to the grid class. In the grid class, go to where we spawned the row and column clearance pieces and clear all valid matches. If count has at least 5 pieces in it, we'll create a rainbow piece. Now we've been setting the color of the special piece to the color of the matched piece, like we do with the row clear and row column pieces, we want to set the color of the rainbow piece to any. Now that we can spawn our rainbow piece, we also need to be able to clear it. We'll do this in swap pieces. Remember that the rainbow piece can be swapped with any piece, even if it doesn't form a match. In swap pieces, when we check if the swap forms a match, we'll also check if the type of one of the pieces is rainbow. That way, even if the swap doesn't form a match, we'll still clear the pieces. Because the rainbow piece can be swapped with any piece, it won't be found as a valid match when we call clear all valid matches. That means we need to clear the rainbow piece manually after we move it. We check if piece 1 is a rainbow piece and is clearable, and if piece 2 is colored. If so, we get a reference to the clear color piece component from piece 1. We set the color of the clear color piece to the color of the matched piece. The reason we have to get the clear color piece component directly here, instead of using the reference stored in the game piece, is because the game piece stores an object of type clearable piece. That means we can only access members of the base clearable piece class through that reference. Since the color variable is only defined in the clear color piece derived class, we need a reference to that. After setting the color, we clear the rainbow piece. Now we check the same thing for piece 2. I'm going to copy and paste and switch all the references to piece 1 and piece 2. Run the game and try to match 5 pieces in a row. You can see that when we match 5 in a row, it creates this new rainbow piece. Swap the piece with any other adjacent piece to clear all the pieces of that color on the board. If you swap 2 rainbow pieces, it will clear all the pieces on the board. Natalie created all these different piece types. We're next going to create some different level types. We can now fill our game board, clear and match pieces, and we even have special piece types. But this still isn't really a game. There's no way to win or lose. We'll fix that by creating a level class, which will keep track of the state of a game. We're going to implement 3 different level types. A timer level, where the player must reach a certain score in the given amount of time. A moves level, where the player must reach a score within the given number of moves. And an obstacles level type, where the player must clear all the obstacles within a specific number of moves. To begin with, we're going to create a base level class that all of our other level classes will derive from. Create a new script called level and open it. This base class will contain all of the things that are shared between all the level types. First, we'll define an enum for the possible level types. Since we know that each level will have a level type, we'll add a variable for that to the base class. This variable will be protected so that the derived classes can also access it. Each level will also need a reference to the grid object, so we'll add a public variable for that so we can define it in the inspector. We'll also need a way to determine how well a player did. We're going to use stars to score the player. I'm going to add 3 public integers which represent the scores needed for each star ranking. We can set these in the inspector later. Lastly, we know each level will keep track of the score, so we add a protected variable for that. Next, we'll implement the functions that every level needs. To start, we need functions to win and lose the game. These will be virtual so that the derived classes can override them if they need to. For now, these will just print debug text. The level also needs to keep track of what the player is doing. create a new function called onMove, which will be called when the player swaps two pieces. We'll add one last function called onPieceCleared, which is called when a piece is cleared. It takes the piece that was cleared as a parameter. Here is where we would update the current score. But how many points do we get? We'll solve that in the next video. When a player clears a piece, they should get some points. Some pieces might even be worth more than others, like special pieces. To know how many points a piece is worth, we're going to add a score parameter. Open a GamePiece script and add a new integer variable called score. Make this public so we can assign it in the inspector. In the editor, click on one of the piece prefabs, and you can see the new score variable. Here you can set how much each piece should be worth. I'm going to make the normal piece worth 300 points. The row and column clearing piece is worth 600 points. And the rainbow piece worth 1000 points. The bubble pieces will be worth 500 points. In the level script, we'll update the score in onPieceCleared. Increment the current score by the piece's score. I'm also adding a debug log so we can see what our score is. Now we just need to call onPieceCleared when a piece is cleared. We'll do that in the next video. We created our base level class with some core functions. Now the level needs to know when the player made a move and when they cleared a piece. The grid class will call onMove to let the level know when the player moved. Open the grid script. First, the grid will need a reference to the level in order to call this function. In the editor, create an empty game object and call it level. Drag on the level script. For now, this doesn't do much. Later we'll be replacing this with components for the different level types. Click on the grid and assign the level object in the inspector. Once the player successfully swaps a piece, we just call the move function on the level. In the level script, add a debug line in onMove. If you run the game, you can see this gets printed each time we swap pieces. You can remove the debug text. Next, we need to tell the level when a piece is cleared. Open a clearable piece script, and in the clear function, call onPieceCleared. We can access the level object through the grid reference. Run the game and make some matches. You can see that its pieces are cleared. The score increments. The last thing we need to do is let the grid know when the game is over, so it stops allowing matches. First, add a boolean called GameOver to the grid class. This is whether or not the game has ended. Also add a function called GameOver to the grid class. The level will call this to let the grid know the game has ended. This just sets GameOver to true. To stop the player from making any more moves, we just need to disable the swap pieces function. We can do this by returning from the function if the game is over. Now we just call the grid's GameOver function when we win or lose the game. Now we're ready to implement our first level. Our dam will have several different levels. Each level is going to be its own scene. Duplicate the main scene, and we name it to level 1. By having each scene as a separate level, we can adjust the parameters of the grid and level objects per level. Open the level 1 scene. Right now our grid object always spawns some bubbles and these spots. We want to be able to adjust what type of pieces are spawned at the beginning of the level and where they're spawned. We're going to create a variable in the inspector where we can specify what pieces to spawn when we start the game. Open the grid script. For each piece, we need to know the type of piece and the position where it should be spawned. Create a new struct called piecePosition to store these values. Make the struct serializable so we can view it in the inspector. Then add a public array of these piecePosition structs and call it initial pieces. If you click on the grid object, in the inspector you can see our new array. Add a few bubble pieces in different positions and hit play. The bubbles are still in the same positions as before. because we haven't yet written the code to spawn pieces from the initial pieces array. We'll do that now. In the start function of the grid, go ahead and remove where we're spawning the bubble pieces. Then, before we spawn the empty pieces, we'll loop through the array of initial pieces and spawn new pieces of that type at the given position. We check if the position of the piece is within the bounds of our grid, and if so, we spawn a new piece. Now we don't need to spawn empty pieces at the spaces we just filled. Before spawning an empty piece, check if the piece there is no. If the piece is no, it means there's not already a piece there, and so we spawn an empty piece. I'm going to change the start function to awake. Later on, for our obstacle level type, we'll need to access the pieces in the grid when we start the level. To make sure that all the pieces are created, we'll do this in awake. Hit play, and now our bubbles are spawned at the positions we specified in the inspector. Now we're ready to implement the different level types. The first type of level we're going to implement is the number of moves level type. The player will start with a certain number of moves and a target score they must reach. If they reach the target score within the given number of moves, they win. If not, they lose. Create a new script called level moves and open it. This will derive from our base level class. The only additional parameters the move type level moves over the base level is the number of moves the player gets, the target score, and how many moves the player has already used. The number of moves and the target score will be public, so we can set them in the inspector. In start, we set the level type to the moves level type. We'll also print the number of moves and the target score. Later, we'll be implementing a UI to display this. In the level 1 scene, click on the level object and remove the level component. Replace it with the level move script. Assign the variable for a grid object in the inspector. Click on the grid and change the size to 6 by 7. Drag in a reference to our level object, and then clear the initial pieces array. This level is not going to have any bubble obstacles. Now we'll implement the logic for the level. We just need to override the onMove function. When the player makes a move, we increment moves used. Then, if the number of moves minus the moves used is 0, it means the game is over. Depending on if the current score is high enough, we either call game win or game lose. We'll also add some debug text so we know how many moves we have left. The biggest challenge with designing levels is deciding what values to put for our number of moves and target score. We don't want the level to be too easy, but we also want to make sure it's not impossible. What you can do is decide how many moves you want the level to last for, and set the target score to something impossibly high, like 5 million. Then play the level several times and see how many points you are able to get in that number of moves. You can use that data to determine what the target score and 1, 2, and 3-star scores should be. A more sophisticated way is to create an AI that will play the level and create lots of data that you can use to determine the score. That's outside the scope of this course, but feel free to try implementing it on your own. I chose 14 moves and a target score of 15,000. The scores for 1, 2, and 3 stars are 15,000, 18,000, and 21,000. I've entered those values in the inspector. You can adjust them if you want the level to be easier or harder. As you play the game, you can see the number of moves left decreasing. When it reaches 0, you either win or lose the game. I had a final score of 28,300, so I won. The next type of level we're going to implement is the obstacles level type. The next level type is similar to the number moves level, except instead of trying to reach a target score, we have to clear all the bubbles of the grid. Create a script called level obstacles and open it. Make it derive from the base level class. Like the moves level type, the obstacles level type also needs to know the number of moves the player has and the moves already used. We also need to know which pieces are obstacles. Add a new array of piece types called obstacle types. Finally, we need to know how many obstacles are remaining so we can check when they're all cleared. Create an integer called numObstaclesLeft. In start, we set the level type to the obstacle level type. We then need to count how many obstacles are in the grid. To do that, we need to add a function to the grid class. Open the grid class and create a new function which returns a list of game pieces. Call the function getPiecesOfType. Have it take a piece type as a parameter. This function will return a list of all the pieces on the board of the given type. We created a list to hold the pieces and then loop through all the pieces in the grid. If the piece type matches, then we add it to the list. Finally, we return the list. Back in the level obstacles script, in start, we loop through the obstacle types and get all the pieces of that type from the grid. We then increment the number of obstacles left by the number of pieces in the list. Next, we'll override onMove like we did with the moves level type. Each time the player moves, we increment the number of moves used. If the player has no moves remaining, but all the obstacles haven't been cleared, then the player loses the game. I'm also going to add a debug log of the number of moves left. We need to know when an obstacle is cleared, so we can decrease the number of obstacles remaining. Override the onPieceCleared function. We'll still call the base function, so that the scores will get updated. Then we loop through the obstacle types and check if this piece matches any of them. If the cleared piece is an obstacle, then we decrease the number of obstacles left. If all the obstacles have been cleared, then we won the game. For each move the player has left, we'll give them 1,000 points. Then we call game win. Let's create a new level that uses the obstacles level type. Duplicate a level 1 scene and rename it to level 2. Click on the level object and remove the level move script. Add the level obstacle script instead. Drag on the reference to the grid. And set the obstacle types array to have just one element, our bubble piece type. Next, we'll modify the grid to start with some bubbles on it. On the grid object, assign the level reference and set the size to 9 by 9. Then we'll add our obstacles. I'm going to add the bubbles in an X shape, but you can do whatever you want here. For my level, I think 10 moves is an appropriate number. The star scores will be 25,000, 27,000, and 30,000. I'm going to set these values in the inspector for the level class. Try to level out and see what you think. You can make the level easier or harder by changing the number of obstacles and where they are, or by adjusting the number of moves. Try making a few different obstacle levels. Now all that's left is our final level type, the timer level. The last type of level is the timer level, and we're going to make a new script called level timer. Like the other level types, this will derive from the base level class. The timer level means to know how much time the player has in seconds and what the target score is. I'm also adding a variable called timer, which is how long the game has been running for. The level type is levelType.timer, and I'm just going to add some debug text to tell the player how much time they get and the target score they need to reach. An update will update the timer. If we run out of time, then we check if we reached the target score. If we did, we won the game. If we didn't, we lost the game. Duplicate the level 2 scene to create level 3. This will be our timer level. Replace the level obstacles component with the level timer script we just made. Drag in the reference to the grid. I'm going to give the player 90 seconds to reach a target score of 50,000. The star scores will be 50,000 for 1 star, 65,000 for 2 stars, and 75,000 for 3. On the grid object, drag in a reference to the level object, and then clear the initial pieces array. This level won't have any bubbles on it. Set the dimensions to 8 by 8. Play through the level and try to reach the target score in 90 seconds. In the console, you can see that I won the game, but it's calling game win over and over again. That's because even after the game ends, the timer keeps counting down. We need to add another variable called timeout, which will let us know when the game is ended. We'll only decrease the timer if the game hasn't ended yet. That finishes up all the different level types. Next will be implementing the user interface.
The HUD, or heads-up display, will let the player know important information while they're playing the game. For our game, this will be things like the number of moves left, the target score, and the player's current score. You can find all the assets for the user interface in Textures UI. Open the Level 1 scene. Create a new UI image by going to Game Object, UI, Image. You'll have to zoom out a lot to see the UI canvas. The canvas is the thing that draws our UI. In the inspector, set the UI scale mode to scale with screen flies. This way, our UI won't get cut off even on smaller screens. Set the reference resolution to 1920 by 1080. This is the resolution I used when I generated the UI assets. Our HUD will have 3 elements: the remaining moves or time, depending on the level type, the player's current score and how many stars they have, and the target score or number of obstacles left, again depending on the level type. We'll start with the number of moves or time remaining. You don't have to use the exact same values for your UI as I'm using. Just move things around until you get it how you like. I'm going to clean the empty child under the canvas. Make sure to undo the canvas object and rename it to remaining moves/time. Make the image a child of this game object and rename it to remaining BG. This will be the background for this element. In the inspector, change the sprite on the image to our small rectangle. In the bottom here, you can see the native resolution of the texture. Start by setting the width and height of the transform to this size. You can always scale this down later, but we want to make sure that the proportions are correct. Anchor this to the top left. This means our position will be relative to the top left corner of the screen. Move an image around and resize it until you get it how you like. Next, we're going to create a text object. Making a child of the remaining moves/time object. Rename this to remaining_text. This is where we'll put how many moves you have left or how much time is left. Now, the default font is Arial. We're going to import a different font from the standard assets. Go to Assets, Import Package, Utility. Click the None button, and then scroll down until you find the Open Sans folder. Check the box next to it and click Import. This will import the Open Sans font into your project. Now we can change the font on our text object to Open Sans Bold. Again, change the anchor to the top left and move the text object over the background. You can see that the font is really small, so increase the font size until you get it how you like it. I'm going to center the font and align it on our background. I'm also going to change the color. Duplicate this text object and rename it to remaining subtext. This is where we'll let the player know what this number actually means. For example, something like remaining moves. Make this text much smaller and put it below the number. I'm going to make the text box a little bit smaller so that it wraps, and I'm going to decrease the line spacing. You can see that the text on top got kind of weird. This just happens sometimes in Unity, so just go over and retake the text and it'll fix it. You can preview how the UI will look by going to the Game tab. Now I'm going to duplicate the remaining moves object and reuse it for our target object. Rename the object to target. Also rename all these sub-objects. Then go ahead and select them all and drag them down so they show up below the remaining object. I'm going to update the subtext to something like target score. Finally, we'll create our score object. Create a new empty child game object, make your child of the canvas, and rename it to score. Then create a new UI image. Make that a child of score and anchor it to the top left. Now for the sprite, we're going to use our small square. Again, set the width and height to the image size. Then move it over below our target object and resize it. Rename this to score BG. Create another image, make it a child of score, and name it star 0. This will display how many stars the player has. Change the anchor to the top left and the sprite to stars underscore 0, setting the width and height to the image size. Go ahead and position this over the background. Duplicate the star 0 object 3 times, and rename these to stars 1, stars 2, and stars 3. For stars 1, set the sprite to stars underscore 1. For 2, stars underscore 2, and for 3, stars underscore 3. We'll hide or display these images depending on the player's score. Finally, create a new text object. Make it a child of the score object, then rename it score underscore text. Anchor it to the top left, and change the font to Open Sans Bold. Position it over the background and adjust the font size. Social the text and change the color to match our other text objects. I'm going to check the best fit box. This will scale the text so that it fits within the box. That way, if a player has a really high score, it won't run outside the dimension of the text box. I'm going to split the max size to 115 and the min size to 80. This means it will automatically scale the font to somewhere between 80 and 115 so that it best fits inside the box. This gray box is the bounds of the canvas. You can see that our score element goes outside of this a little bit. So I'm just going to rescale everything so that it all fits. Next, we'll create a script to update the HUD. Now that we've created all the UI elements for our HUD, we need to update the values to match the game. We'll create a script with functions that will update our UI elements. Create a new script called HUD. First, we'll add a variable to store a reference to the level. Then we'll add variables to store references to all of the UI elements that need to get updated. These will be the remaining text, the remaining subtext, the target subtext, the score text, and our star images. The text objects are of type unityengine.ui.text, and the image objects are of type unityengine.ui.image. We'll also add 2 private variables. One of the index of the star image that's currently being displayed. We'll call this star_idx. The other variable is whether or not the game has ended. We'll need this later to display game over screen. In the editor, rename the canvas object to game_UI_canvas. Add the HUD script and hook up all the references in the inspector. When you're done, your HUD component should look like this. Since we'll be using this UI for each level, we'll create a prefab out of it that we can add to all the levels. Drag the game_UI_canvas object into the prefabs folder. Save the scene and then open the scene for level 2. In each of the level scenes, drag in the game_UI_canvas prefab. Also add a UI event system by going to game_UI event system. The only thing you'll need to update on the HUD for each level is the level reference. Repeat these same steps for each of your level scenes. Now that we've added the HUD to each level scene and we've got our HUD script set up, we're going to add some functions to update the UI elements. Now we're going to add some functions to our HUD script to update the UI elements. Open the HUD script. First, we'll fill out the start function. At the start of a game, all we need to do is disable the star images. We loop through all the star images and check that the index is equal to the current star index. This starts at 0, so when the game starts, only the 0 star image will be visible. Next, we'll create a function to set the player's score. We'll call it setScore, and it will take an integer. We set the score text to the score passed in, converted to a string. We have to convert it from an integer to a string because the text parameter expects a string. Next, we have to calculate which star image should be visible. By default, we show the 0-star image. If the score is greater than the score needed for 1 star, but less than the score for 2 star, we show the 1-star image. We do the same for the 2 and 3-star images, checking if the score is within the score range. We loop to the star image array and only am able to start at the same index we calculated earlier, visible star. We disable all of the other star images. Then we store the index of the visible star in star IDX. Now that we've written the function to update the score, let's write functions to update the target text and the remaining text. setTarget takes an integer and simply sets the value of the target text to that integer converted to a string. For setRemaining, we're going to write 2 functions, one that takes an integer and one that takes a string. This is to accommodate our different level types. For the moves and obstacle level types, they'll want to pass in an integer, but for the timer level type, we'll want to pass in a string, which is the formatted time. Both of these functions do the same thing. They set the remaining text to the value passed in. The only difference is that the function which takes an integer has to convert it to a string. The last function we need is one that updates our subtext objects depending on the level type. I'm going to call it setLevelType, and it will take a level type object. Depending on the level type, we'll set the remaining subtext and the target subtext accordingly. For the moves level type, the remaining subtext is moves remaining, and the target subtypes is the target score. For the obstacle level type, the remaining subtext is moves remaining, and the kited subtext is bubbles remaining, since we're trying to clear all the bubbles on the grid. For the timer level type, remaining subtext is time remaining, because we're out limited by number of moves, and the target subtext is target score. The last 2 functions we'll implement are onGame win and onGame lose. We'll use these later when we implement a game over screen. For now, they just set isGameOver to true. That's it for our HUD script. We've written all these functions, but right now nothing is calling them. In the next video, we'll modify the level class to update the HUD. Now our level class just needs to call these functions to update the HUD. First, our level needs a reference to the HUD object. Open the level script and add a new variable for the HUD. Open the scene for level 1 and connect to the HUD reference. Do this for all of the level scenes. Then go back to the level script. In the start function of the level class, we'll begin by setting the score. Since the game just started, this will be 0. In game win and game lose, we'll call the appropriate functions on the HUD. Finally, whenever we update the score, we also have to update the HUD. In onPieceCleared, we can replace our debug text with a call to set score. We still need to call the setRemaining, setTarget, and setLevelType functions. Since these are dependent on the level type, we can't call them from the base level class. Instead, we'll call them in the scripts for each of our different level types. We'll start with the moves level type. In start, we'll call all of the functions to update the HUD. We set the level type to our level type, which is levelType.moves. We set the score to our current score, which will be 0 at the start of the game. We then set the target to our target score, and we set remaining to the number of moves remaining, which right now is num_moves. We can then remove the debug text. Then, when the player makes a move, we update the remaining moves on the HUD. Replace the debug text with hard.setRemaining. Next, we'll call the HUD functions from the obstacles level type script. Open level obstacles, and in start, after we've counted all the obstacles on the grid, we'll update the HUD. Again, we set the level type to our level type, which is levelType.obstacle. We set the score to the current score. We set the target to num obstacles left. Right now, this is the number of bubbles that are on the screen. And finally, we set remaining to the number of moves remaining, which is num_moves. We'll also need to update the target text whenever the number of obstacles changes. In onPieceCleared, after we decrement the number of obstacles, update the HUD. Since we're also updating the score in this function, replace the debug text with the call to set score. The last thing we need to do is update the number of remaining moves just like we did with the moves level type. In onMove, replace the debug text by calling HUD.setRemaining. Just one level type left.
Open up Level Timer. In Start, we update the HUD just as we did with the other level types. We set the target to the target score, and we set remaining to the time remaining. We're going to pass in a formatted string so that the time is displayed in minutes and seconds instead of just seconds. To get the number of minutes, we divide time in seconds by 60. And to get the number of seconds remaining, we do time in seconds modulo 60. You can also delete the debug text now. When we update the timer, we also need to update the HUD. Copy the call to set remaining and paste it right below where we update the timer. Replace time in seconds with time in seconds minus timer. This is the time remaining. Now, since we don't want to display a negative value at the end of the match, we're going to use the max function to get the largest value between the time remaining and 0. That way, if the time remaining is negative, it will just display 0. Then, since the max function returns a float, we're just going to cast it to an integer. Run the game. You can see that some of our text isn't showing up. If you have any text that's not showing up, it's probably because the text is going outside the bounds of the text box. Click on the problem text and increase the size of the text box until the text appears. Hit apply to apply this to the prefab. Since we're using prefabs, this will apply it across all of our levels. Hit play again, and you can see that as we play, the number of moves remaining and our score are updated. Test out each of the different level types and make sure the HUD is working for each of them. In this bubble level, you can see that we're displaying the moves remaining and the number of bubbles remaining. And in the timer level type, we have the time remaining and the target score. Now, since this grid is slightly behind the HUD, I'm going to move it over a little bit. Depending on the size of your levels, you might have to adjust where the grid is. The grid is very small compared to the UI, so you'll have to zoom in a lot. So a HUD works for all of the different level types. Next, we're going to create a game over screen that will pop up when the game ends. Next, we're going to implement the UI for the game over screen. This screen will show up when the game is over. Expand the Game UI canvas object in the hierarchy. Create a new empty child game object and name it Game Over. Create another empty child object under that and name it Screen. We're going to create all of our UI elements under the Screen object. The reason we're creating them under Screen instead of directly under Game Over is because we want to be able to enable and disable the UI elements without enabling and disabling the script, which we'll create later. The script will be on the Game Over object, which means we can enable and disable Screen without affecting the script. Create a UI image, make it a child of the Screen object, and rename it to BG. This will be the background for our Game Over message. You can leave the anchor at the center. Unlike the HUD elements, the Game Over elements are going to be center anchored. Set the sprite to the large rect sprite. Change the width and height of the transform to the native image size. You can reset the background and place it wherever you want it. When the player wins, we want to display their score and how many stars they got. The HUD already has an element that does this. I'm going to copy the score element and paste it under Screen. Go ahead and delete the background. Then select all the objects under Score and change them to be center aligned. Finally, go ahead and move them to the center of the screen and resize them as you like. I'm going to make the score text a bit larger. When the player loses, instead of displaying their score, we're just going to display some text that tells them to try again. Create a new text object and make it a child of Screen. Change the font to Open Sans Bold. Go ahead and resize the element and make the font size larger. I'm also going to center the text. and change the color to match our other text objects. Go ahead and rename this to lose text. The last element we need for our game over screen is two buttons, one to replay the current level and one to go on to the next level. Go to the Game Object menu and select UI button to create a new button element. Make this a child of the screen object and rename it to replay button. You can see that the button automatically starts with a sprite and some text. Replace the sprite with arrow left and set the width and height to be image size. Change the text to Open Sans bold and have it say replay. You can also adjust the size and color. Now I'm going to resize the button and position it at the bottom left of our game over screen. Go ahead and duplicate the replay button and rename it to gun button. Change the sprite to arrow right and change the X position to positive. This will put it in the same spot on the other side of the game over screen. Finally, change the text to say done. Click on the Game UI Canvas prefab and hit apply to apply this to all scenes. Next, we're going to create a quick animation to display our game over screen. Instead of having a game over screen just pop up out of nowhere, we're going to create a little animation to bring it onto the screen. In the animations folder, create a new animation and call it Game Over Show. Drag this onto the Game Over object. As you can see, this added a new animator component and created a new animation controller. Go ahead and double click on the animation controller to open it. Since we don't want this animation to play automatically, we need to make another state the default state. Create an empty state and set that as the default state. Back in the scene, click on the Game Over object and open the animation window. Make sure you're editing the Game Over Show animation. Add a property for the screen object's rect transforms rotation and a property for the screen object's rect transforms anchored position. Go ahead and delete the last keyframe and expand the properties. We want to start with the Game Over screen off the top edge of the screen, so go ahead and adjust the Y position until it's off the screen. Then we want to bring the Game Over screen back to the center. At frame 4, set the Y position back to 0. This moves the screen back to the center. I also want to add a bit of rotation as the screen comes down. At frame 3, set the Z rotation to 0. At frame 5, set the Z rotation to 10. And finally at frame 6, set the Z rotation to 0 to straighten the frame back out. If you scrub through the animation, you can see that the screen drops down from the top and does a little wiggle before settling in the center of the screen. Hit apply on the prefab to apply this to the UIs across all of our levels. Now we're ready to create a script to control the Game Over screen. Now we're going to create a script to control the Game Over screen. Create a new script and call it Game Over. Drag it onto the Game Over object. We're going to add some variables to store references to all the UI elements we need to change. These will be the screen object, the score object, the lose and score text, and all the star images. Connect all of these objects in the inspector. When you're done, it should look like this. Back in the Game Over script, we don't want the screen to be visible when we're playing the game, so in Start, we'll deactivate the screen object. We'll also hide all the star images. We'll re-enable them later. Create a function called showLose, which will be called when we lose the game. When we lose the game, we want to display the Game Over screen, so we set the screen object to active. Then we deactivate the score object, since that should only be visible when we win the game. Then we'll play the show animation we made in the previous video. Now we'll create a function to show the screen when we win the game. Again, we set the screen to active. And we hide the lose text, since that should only be displayed when we lose the game. When we win the game, we want to display the player's score and how many stars they got. So we'll pass those in as parameters to show win. We set the score text to the player's score, and then we hide it. You'll see why in a minute. Then we play the animation to show the screen. We also want to show how many stars the player got, but when we do that, I want to show the stars one at a time. So we'll need to create a coroutine. Create a new coroutine called showWinCoroutine. This will take in how many stars the player got. We'll wait for a moment before displaying any stars. Then we loop from 0 to the number of stars the player got and enable the image. We'll also disable the previous image if there was one. That way, only one image is displayed at a time. We then wait for half a second in between displaying each image. Once all the stars have been displayed, we then re-enable the score text. We'll call this coroutine in showWin. Now we have functions to show the game over screen when we win or lose the game. The last thing to do is implement the functionality for the replay and done buttons. The Unity Scene Manager class lets us load a new scene or get information about the current scene. When the player clicks on the replay button, we'll simply reload the current level. We'll create a function stub for the done button functionality, but we'll implement it later. Now we have to hook up the buttons to call those functions. Click on the replay button object, and at the bottom of the button component, under onClick, click the plus sign. Where it says None, drag in the Game Over object, and from the drop-down, select Game Over on Replay Clicked. When this button is clicked, it will call that function. Do the same thing for the Gun button. Have this one call on Gun Clicked. Hit Apply to apply these changes across all of our levels. Now, we just need to have the level call these functions when the game is over to show the Game Over screen. Now that we've created our functions to show the Game Over screen when we win or lose the game, we need to call these functions from the HUD. Open up the HUD script. The HUD already knows when we win or lose a game because the level is calling the on-game win and on-game lose functions. This is where we'll show the Game Over screen. Add a variable to store a reference to the Game Over screen. In the inspector, assign the reference to the Game Over screen. Click Apply to apply to the prefab. In onGameWin, we'll call Game Over .showWin, and we'll pass in the score and star IDX, which is the number of stars the player got. In onGameLose, we'll call Game Over .showLose. Unity will give you a warning when you've created a variable that's not being used. Since isGameOver ended up never being used, let's go ahead and remove it. Hit play and finish a game. The Game Over screen popped up, and it shows how many stars we got and our score. Right now, the Game Over screen appears as soon as we run out of moves. But at this time, the board might still be refilling and clearing pieces. We should wait until the board is finished filling before we show the Game Over screen. In the Greet class, add a variable called isFilling. This boolean will tell us if the grid is currently filling or not. Then at the start of the fill function, we set isFilling to true. And at the end of the function, we set it back to false. Now when we win or lose a game, we'll have the level wait until the grid has finished filling before letting the UI know. Open the level script. Add a boolean called didWin. This is whether we won or lost the game. In game win, move the call to HUD.onGameWin and the debug text, and set didWin to true. In game lose, remove the call to HUD.onGameLose and the debug text, and set didWin to false. Now we're going to create a coroutine that will wait until the grid is finished filling. While the grid is filling, we wait. Yield return 0 waits for 1 frame. Once the grid is done filling, we check if we won or lost. If we won, we call HUD.onGameWin and pass in the current score. If we lost, we call HUD.onGameLose. Now in GameWin and GameLose, we'll call our function to wait for the grid to finish filling. So that our inherited classes can access this function, we need to make it protected. Go ahead and play another game. Now when the game ends, we wait until the board has finished filling before showing the Game Over screen. All of our game UI is now done. Next, we'll be creating a level select screen so that players can switch between different levels. The last thing we need to do is create a level select screen so that players can switch between different levels. Create a new scene. Save it in the Scenes folder and call it Level Select. Create a new UI image. Since this screen will just be made up of UI elements, you can delete the main camera. First, let's set up the canvas. Just like we did with the HUD, set the US scale mode to scale with screen size, and the reference resolution to 1920 by 1080. Click on that image, and change the sprite to BG2. Set the width and height to 1920 by 1280, since this is the texture's native resolution, and set the anchor to the bottom center. Align the texture to the bottom edge of the screen. You can see that the background looks good at some resolutions, but at others, there's empty space. We need to click on our canvas, and under Canvas Scaler, slide it to match the height of the screen. Now our background completely fills each resolution. We name the image to BG. Create a new button. This will lead the button to select a level. Change the sprite to Stone Square. Set the width and height 193 by 185. Create a new image and make it the child of the button. For the sprite, select 1 and set the width and height to 32 by 51. Center it by setting the X and Y position to 0. Then go ahead and delete the text object. This number represents what level this button will load. We're going to add another image and make it a child of the button. Change the sprite to Star Small and set the size to 45 by 40. This represents how many stars the player earned on the level. Drag it over top of the background. Duplicate this image twice and align the stars so they're next to each other. Select them all and center them on the button. Go ahead and adjust the number and the stars until you get them where you like them. Then go ahead and rename the objects to something more meaningful, like number, star 1, star 2, and star 3. Since we have 3 levels, we'll create 3 buttons. Go ahead and duplicate the button twice and place them next to each other. Change the number sprite on each one to correspond to the number of the level. A level select UI is ready. Now we just need to load the appropriate level when we click on a button. Now we'll add the functionality to load a level when we click on the button. Create a new script called Level Select. Drag it onto the canvas object and rename that to Level Select Canvas. Open the Level Select script. We'll add a function that gets called when a button is pressed. Call it onButtonPress, and it will take the name of the level to load as a parameter. Now we just use the Scene Manager to load that level. Go back to the editor. Click on a button, and under OnQuick, click the plus and drag in the Level Select canvas. From the dropdown, select the Level Select onButtonPress function. For the string, take in the name of the level you want to load. Since this is the button for level 1, I'll type level 1. Do the same for the other two buttons. Hit play and click on a button. You see we get an error that the scene could not be loaded. That's because we haven't added our level scenes to the build settings. Go to File, Build Settings. Drag in the level scenes and the level select scene. Close the build settings and run again. You see that when we clicked on the button, it loaded the level. Now we just need to get back to the level select screen after we finish the level. Open the Game Over script. Remember we added a function stub for when the gun button is clicked. Here, we'll load the level select scene. Hit play and load a level. Finish the game until the Game Over screen shows up. Try clicking on the gun button. You can see it brings us back to the level select screen where we can select another level. The final element of the level select screen is the stars. We want to display the highest score the plan has achieved for each level. We'll do that next. We want to display the highest number of stars the player has earned on a level in the level select screen. First, we need to store the player's highest score. Open the HUD script. Since we only want to store the score if the player won, we'll store it in on-game win. .idx is the number of stars the player got. We'll be storing the score in player prefs. First we check if the currently stored score is less than the new score. For the key, we'll be using the name of the currently loaded theme. I'm going to set the default value to 0. That means if the player hasn't completed a level yet, and there's no score stored, this will return 0. If the new score is greater than the stored score, then we store the new score. Now that we're storing the highest score, we can access it in the level select script. Go ahead and open that up. We'll need references to all of the button objects so that we can show or hide the stars depending on the player's score. We also need to know what player pref key is associated with each button. Create an struct to hold those values. Mark this as serializable so we can view it in the inspector. And then create an array of these structs. In the editor, click on the level select canvas. Assign each of the buttons to the array. And set the player pref key to the appropriate value. Remember, this is the name of the scene for each level. Now in Start, we'll loop through the array of buttons and get the highest score for each one. We'll then show or hide the stars accordingly. We get the score for each level, passing in the player pref key we specified in the inspector. We then loop from 1 to 3 and get each of the stars. We do this by using transform.find, star, and the current index. This will search for a child of the button with that name. If the index of the star is less than or equal to the stored score, it means that the player has achieved this star ranking, and so we enable the star. If this star index is greater than the player's score, it means they haven't yet achieved this star ranking, and so we hide the star. Hit play. You can see that all of the stars are hidden. Complete one of the levels. Click Done to go back to the level select screen. And you can now see that I have a score of 3 stars on level 1. That's it for the level select screen. While I only have 3 levels, I encourage you to make lots of different levels and fill this screen out. It's your game, make it how you want it.
I hope you've enjoyed this course and that you're ready to take your game to the next level. As you bring this game closer to release, here's some things you might want to consider. While we've covered a lot in this course, there's many more things you can do to polish your game. For example, right now we don't reshuffle the board when there's no possible matches. You'll probably want to shuffle the board so that the player doesn't get deadlocked. You might also want to make it so that the initial board doesn't have any matches on it, so that pieces don't get cleared right as the game starts. There are many more features you can add to your Match-3 game. Most Match-3 games have many more piece types than what we've implemented here. You might want to implement a special piece that clears all pieces in a box around it, or make it so that when you swap two special pieces, they combine for an even bigger effect. If you're interested in taking this game to mobile platforms, then check out my course, Creating Mobile Games with Unity, which shows you how to prepare a Unity project for release on mobile. If you're interested in doing more 2D work with Unity, there are several courses specifically tailored to that. You might want to check out Unity 5 2D, Optimizing Graphics, Unity 5 2D, Generate Procedural Terrain, or Advanced Unity 2D, Sprite Palette Swapping. If you want to learn more about scripting in Unity, try my other course, Scripting Unity in C# or Advanced Unity 3D Game Programming.